Okay, welcome to another DEA video. This one we're going to be talking about return to scale. So in the very first video, as I was sort of presenting everything, um, we had a kind of chart of output versus input, assuming one output and one input, and we sort of drew this line representing the efficiency frontier as having the steepest ratio of output to input, which gives you sort of the steepest slope to that line. Okay, and we said C was the only DMU that was on that efficiency frontier, but we could make targets for each of the other DMUs along that efficiency frontier. Baked into how we did this was the idea that we could scale down C, which is essentially the DMU that was defining our efficiency frontier, that we could scale it down arbitrarily small. And so, for example, I believe the target for A was 25% of C, both in input and output. And the target for D was 133% of the input and output of C. And so baked into kind of the underlying assumptions was that we could scale C up or down. Now in practice, if you've got your DMUs being sort of production workshops or something like that, there might be a point where you can't scale the inputs down any farther and not have something that just doesn't make sense. Similarly, you might not be able to scale up without adding kind of extra costs. Or sometimes you gain things when you scale up. And so this sort of keeps the idea that you have what are called this assumption is called constant return to scale, in that you can scale up and scale down proportionally, and that's just fine. Now let's explore maybe some other options. Okay, so constant return to scale. And so let's kind of recreate that plot, and I'll redraw that line. And that line goes through C. It's sort of the steepest one here. And that's the efficiency frontier for what's called constant returns to scale. So we'll call that CRS. Now, that's okay, but it bakes into this idea that you can scale up and scale down. Now, an alternative to that is what's called variable returns to scale. And variable returns to scale says that we're going to put limits and that you can't really arbitrarily scale things up and down, but your target should always be the same essential size as the DMUs that you already have. Okay, and so what that does is it puts constraints on your lambdas. Okay, so here let's have RTS stand for returns to scale, and constraint. And so for constant returns to scale, there's no constraint on your lambdas. Okay. For variable returns to scale, abbreviated VRS, we get a constraint that lambda A plus lambda B plus lambda C plus lambda D. So our kind of our weights in that make up our target, the sum of those has to equal 1, which means that our target will always be what's called a convex combination of our other DMUs. Okay. Visually, what that works out to looking like is that we can make a target that is sort of along the line between any two DMUs. Okay. And so in this case, our efficiency frontier is everything along this line is going to be a convex combination of A and C. Anything along this line is going to be a convex combination of C and D. If we go beyond that, then we sort of don't gain any extra output, or if we go below that, we don't gain any extra input. And so these lines are what we call variable return to scale. And if we enforce this constraint on the lambdas, this is essentially our efficiency frontier for variable returns to scale. And so when you choose variable returns to scale, you're going to end up with more DMUs that get counted as being the most efficient, because you can now be efficient by having a really good ratio of inputs to of outputs to inputs, or by being very small, or by being very large, and still being relatively good in your ratios. And so D sort of has the most output, and because of that, it automatically becomes efficient. A has the least amount of input, and because of that, it becomes an efficient DMU. C has the best ratio of output to input, and so it's an efficient DMU. Under variable returns to scale, B is still not very efficient, and so it is not an efficient DMU. Okay. So this restricts us and says we can't really scale down to make our target, or scale up to make our target, but our targets have to be a convex combination of the other ones, and that the total weight has to add up to 1. Now there's a couple of other options that we can have for returns to scale. We can have increasing returns to scale. This allows us to scale up but not down. And so that would say that the sum of our lambdas has to be bigger than or equal to 1. So if you think that it's fair in your scenario to scale up but not scale down, you'd use increasing returns to scale. There's also the opposite, which is decreasing returns to scale, where you're allowed to scale things down but not up to create your target efficient DMU. Okay. These are maybe the most common ones. There's a couple other ones out there, and if you poke around the DEA benchmarking package that we've been using, you'll see that there's a couple called free disposability hull and things like that. So let's see. We'll use a couple more colors here to add them to our plot. For decreasing returns to scale, we're allowed to scale down. That's maybe the easiest one to think of. And so we're always allowed to scale C down, and so we can scale C down along this line. But then after that, we can't scale C up anymore, and so we got to use a combination of C and D, and then past that D. And so this gray, that was decreasing returns to scale in the gray. And then I've got one more color for blue, and that's increasing returns to scale. And that one would sort of follow this part here, and then would follow off along that line. And that would be increasing returns to scale in the picture. In that the idea maybe there is that you can always scale anything up. And so here we can kind of scale up along here. Here we can kind of scale off to infinity and make a larger version of C if we want to. Kind of thinking about it of the slopes is that the slope starts off infinitely steep and then gets a little bit shallower between A and C, and then gets shallower here, but then it doesn't go below that. So I'll kind of show you what this looks like in R using the benchmarking package. It's really easy to switch between those different returns to scale. If you were doing this manually by formulating this as a linear program, if you had constant returns to scale, you wouldn't add any constraint. But for each of these other ones, you would add the corresponding constraint that put a limit on the size of the sum of the lambdas. Okay. So let me share what this looks like in R with that benchmarking package. So easiest to see this on a one input, one output model. And so we'll return to the one input, one output model. Here's where we have a choice to change the returns to scale, and we'll mostly just look at this. So here's our constant returns to scale, CRS. and we just get the one line with that slope. If we switch this to VRS for variable returns to scale, we'll see that it sort of follows the hull of A, C, and D, and so you can kind of the way I visually think about it is you kind of lay a string down over top, and whatever it catches on are the most efficient DMUs. Okay, and that's kind of what it looks like as you look here. Okay, if I go down to actually solving the DEA model and change the returns to scale to VRS and run this, you'll notice now that our efficient DMUs, A, C, and D are all efficient. B is still not considered efficient even when you use variable returns to scale. Okay. And sort of the target for B is now 89% of A and 11% of C. Notice that the sum of the weights in each of these rows adds up to 1 exactly. Okay. You'll and sort of the targets are now going to be a little bit different than they were under a constant returns to scale, because the targets are going to be along this efficiency frontier rather than the previous efficiency frontier. Okay, which makes pretty much all of the DMUs look more efficient. Okay, so going from CRS to VRS, everybody should look better because you've sort of added a restriction to your lambdas. Okay, so that's variable return to scale. Let's look at increasing return to scale with IRS. And so here we go up to A, over to C, and off to infinity. Okay, so that's increasing returns to scale. And if we switch that in the solver, we'll see that A and C are efficient, but D and B are not. We can also do decreasing returns to scale. So increasing allowed us to scale up, okay, and even scale that sort of off towards infinity. It's maybe not easy to tell, but there is a slight bend in the line from A to C versus C off to infinity, I think. Oh, maybe that is a straight line. No, I don't think so. Now we can do DRS for decreasing returns to scale. Here, it's essentially like you add an extra DMU that is at 0, 0. And so you go from there until the first one that you would hit would be C, and then off to D, and then off towards infinity. And so now C and D are the efficient DMUs. And so if you change that over here to DRS and run it, we should see that the efficiencies for C and D are 100%, but A and B are less than 100% efficient. Okay, so that's it on returns to scale. The question that you want to ask yourself as you're sort of modeling with the DEA is it fair to scale down? Is it fair to scale up? Or is it not fair to scale at all? And everything should be essentially but similar size to the DMUs that you have when you're making a target. It should be sort of an interpolation between DMUs. Okay, so that's really what's happening in the VRS is that you're only allowed to make targets that are interpolations between your DMUs. So that's it for this video.